In this video, we'll be looking at motion in 2 dimensions or projectile motion. So we'll be looking at motion in 2 dimensions. So motion in 2 dimensions, or what we call, projectile motion. Right? So motion in 2D or projectile motion. Now, in our look at motion so far, we've basically restricted the situation to bodies moving in only 1 dimension. So we've looked at bodies which moved horizontally along the ground. So for instance, a car or a bicycle. And we've basically examined their distance time graphs, displacement time graphs, speed time graphs, and velocity time graphs, and so on. We've also derived equations of motion for uniform acceleration, right? Now, we've also then looked at bodies which are moving vertically. And we said that these same equations of motion for uniform acceleration could be applied to bodies which are moving vertically, if certain things are taken into consideration, right? Like, for instance, when the body is moving vertically, the acceleration is the acceleration due to gravity, right? So in our look at motion thus far, we basically restricted the situations in which bodies only moved in one dimension. They either moved horizontally or vertically, but not both, right? However, in our look at 2D motion or projectile motion, we'll be examining bodies which are not only moving horizontally, but also moving vertically at the same time, right? Now, experiments have shown that basically, if a body is moving horizontally, then its horizontal motion is not affected or does not affect its vertical motion. So if a body is moving both horizontally and vertically, its horizontal motion is not affected by and does not affect its vertical motion. So essentially we can say that the vertical motion and the horizontal motion are independent of each other and therefore do not disturb each other, right? Now, a simple experiment can basically be done to demonstrate this. Now let's say we have a desk or a table. So we have a desk or a table, and there is some ramp on the table from which a ball will roll, right? So the ball will roll along the ramp and then will be projected from the table, right, with some speed, right? So let's say the ball's path will continue like that. Now let's say that simultaneously another ball will be dropped from the same vertical height. So another ball will be dropped from the same vertical height. So simultaneously, when this ball leaves the edge of the table, another ball will be dropped from the same vertical height. Now, if multi-flash photographs of the motion of these 2 balls are taken, then what it will basically show is that at every stage of the 2 balls motion, they're at the same level, right? So if when this ball reaches here, then the ball which is basically dropped will be at the same level. Likewise, the same level, right? And they will also strike the ground at the same time, right? So the 2 balls will strike the ground at the same time. So what this basically shows is that despite the fact that this ball only moved vertically, whereas this ball is moving both horizontally and vertically, the horizontal motion of this ball did not affect its vertical motion. So if 2 identical balls are released in this situation and multi-flash photographs of the ball's motion are taken, then what this reveals is that at times, then the balls will basically move at the same rate vertically, despite the fact that one ball is also moving horizontally, right? And these experiments, of course, have been used to basically demonstrate or to conclude that the body's vertical motion is independent of its horizontal motion and therefore does not affect it or is not affected by it, right? So this basically becomes very important when dealing with projectiles, because as we know, projectiles not only move horizontally, but they move vertically as well. Now, what exactly is a projectile? When we think of a projectile, we basically think of an object flying through the air at a certain speed, right? And we can actually think of some objects like that. So examples of projectiles, for instance, a football being kicked in a match. So it could either be kicked by the goalkeeper who's taking the goal kick, or it could be, for instance, a free kick taken in an attempt to score. So a football moving through the air is an example of a projectile. Another example of a projectile, of course, is a golf ball moving through the air after being struck by a golfer in an attempt, of course, to get it into the hole, right? In the game of tennis, of course, the path of the tennis ball makes it a projectile as well. A bullet being fired from a gun is also a projectile. A javelin being thrown by an athlete is also an example of a projectile, right? But we basically say that a projectile, which is anybody which is given some launch velocity and then moves under the action of its weight only, right? So projectiles are usually given some launch velocity with which they start to move, and subsequent to that, the only force which is acting on them is their weight. So say a projectile is a body which is launched with some velocity and then acts under its own weight only, right? Now, that is a projectile. So we've talked about examples of projectiles, and of course we've stated exactly what a projectile is. Now let's examine in greater detail the characteristics of projectile motion. So we'll look at the characteristics of projectile motion. So characteristics of projectile motion. Now, a projectile, basically, it will move with a constant speed. So we could say that a projectile motion is motion which the body moves with a constant velocity in one direction, and let's say, for instance, that is horizontally. So the body moves with a constant velocity in one direction and a uniform acceleration in a perpendicular direction. So in a perpendicular direction. And if we're talking about horizontally, then the perpendicular direction is, of course, vertically. So when we're talking about projectiles, we're talking about a body which moves with a constant velocity in one direction, usually the horizontal direction, but as a uniform acceleration in the vertical direction, right? So with a projectile motion, the only force which acts on the body, so the only force acting on the body is its weight, right? And of course, you know that the body's weight acts vertically downwards, so the only force acting on the body is its weight, and its acceleration is the acceleration due to gravity. Right? And of course, during projectile motion, the effects of wind resistance are ignored. Right? So those are some characteristics of projectile motion. Now let's basically look at the case of a body which is projected or launched at some angle to the horizontal, right? So we say consider a body which is projected with velocity v at some angle theta to the horizontal and returns to its initial level of projection. Right? So let's examine such a body. So let this be the path of the body. And let's call this point O from which it's projected, and this point A. Right? So the body is projected with a velocity v at some angle theta to the horizontal. So this velocity, of course, will be tangential to the actual path that the body is traveling. Right? So looking like a, let me draw it better. Right. So this is the body's velocity v at some angle theta to the horizontal. Right? So as I said before, a projectile must be given some initial velocity, subsequent to which it will then move under the action of its own weight. So the velocity, or the projectile in this case, is launched with a velocity v at an angle theta to the horizontal. Now as the body travels, or as the body moves, its vertical velocity will change, but of course its horizontal velocity will remain constant. Now let's examine the initial vertical and horizontal components of this body's velocity. So resolving the body's velocity into its components, we'll see that it will have a vertical component and a horizontal component. The vertical component is given by, so this angle of course would be theta, would be the horizontal, right? So the vertical component is given by v sine theta, and the horizontal component is given by v cos theta. Right? Now we're dealing with motion in two dimensions. So the body is moving horizontally as well as vertically. Now we say that horizontally the body velocity is constant because horizontally there's no resultant force acting on the body. Or we say that no force acts on the body which has a component in the horizontal direction, and we ignore the effects of wind resistance. So therefore, throughout the body's flight, the horizontal component of the velocity will be constant, and the horizontal velocity will be equal to the initial component or the horizontal component of the initial velocity. However, because the body is moving vertically, it will be accelerating, and the acceleration will be the acceleration due to gravity. Now we looked at vertical motions before, and we learned how to apply our sign convention. So if a body is projected vertically upwards, we say that the upward direction is taken as being positive, and the acceleration a is equal to minus g. Now as the body moves up, because of this acceleration being negative, its vertical velocity will decrease. So if we were to use the length of these arrows as a relative magnitude of these velocities, then at some point, say between O from which a body was launched and say the maximum point, let's call this point, so this is A, let's call this point here B. So B is basically the maximum height or the top of the parts of the body's trajectory, right? Now between O and B, then as we mentioned before, the horizontal velocity will have the same component, but the vertical velocity will have decreased somewhat due to the acceleration being equal to minus g. Right? So the vertical component has reduced in magnitude, but the horizontal component remains the same. Now at the top of the trajectory, the body is no longer moving vertically, so it is only moving horizontally. So therefore it only has a horizontal component. So let's call this Vx, and this is Vx. And at the top, Vy is equal to 0, right? Now as the body moves downwards, obviously it changes direction, and it will start to speed up once again in the vertical direction. So this time, of course, it will have a vertical velocity, but in the opposite direction. So at this point, it will still have a horizontal velocity given by Vx, and it will have a vertical velocity Vy. And eventually, when it reaches back at its initial level of projection at A, it will have regained its initial velocities, both horizontal and vertical. So this is Vx, Vy, right? So when the ball or when the body returns its initial level of projection, it would have acquired or regained its initial velocities, initial vertical velocity, because of course the horizontal velocity remain constant, right? So basically, as I said before, as the ball rises, its vertical velocity decreases, and at the top of its trajectory or the maximum height, the vertical velocity is equal to 0, as the ball is no longer moving vertically but only horizontally. It then falls and regains its vertical velocity, and when it returns to the initial level from which it was projected, we say that it has regained its initial velocity, the vertical value, and of course we know that the horizontal value would have remained constant throughout its entire path, or throughout its entire flight, right? Now, having looked at that, we will then derive expressions for certain properties of a path like that which are commonly used, right? So certain characteristics, like for instance maximum height, time to reach maximum height, and so on, are very commonly or frequently calculated, and as such we will derive expressions which will easily allow these things to be calculated. Now before we go into that, we will analyze the horizontal and the vertical motion, and then we will look at the equations which apply in each direction. So let's look at the horizontal direction. So we'll say that horizontally, the resultant force is equal to 0. So the resultant force is equal to 0, which of course means the acceleration is equal to 0, and therefore the velocity is constant. So we'll call the horizontal component of the velocity Vx. So Vx is constant and given by Vx is equal to V cos theta, right? So at any point during the body's flight, its horizontal velocity is given by V cos theta, which is the initial horizontal component, or the horizontal component of its initial launch velocity V, right? So again we say that horizontally the speed is constant, the velocity is constant, and given by that. And because speed is constant, generally we can say that, since speed is equal to distance traveled over time taken, then it simply means that distance traveled, or just distance, is equal to speed by time. So what does this mean? It basically means that at any time t during the body's flight or during its motion, its horizontal distance traveled, let's call that x, is equal to the horizontal velocity Vx times the time t, right? So at any time t during the body's flight, the horizontal distance traveled is simply given by the horizontal velocity Vx time t, but of course Vx is equal to V cos theta, so we can say that Vx is equal to V cos theta times t, which is the same thing as Vt cos theta, right? So at any stage of the body's motion, its horizontal velocity will still be given by that, right? Good. Now let's look at the vertical direction. Now vertically. Now we said that vertically the body is accelerating, and the acceleration a is equal to minus g, because of course we're talking about the vertical motion and we're using the sign convention that up is positive. So therefore, if up is positive, while it's so vertically, so we know that A is equal to minus G. So the acceleration due to gravity is equal to, the acceleration A is equal to minus G, where G is the acceleration due to gravity, the value of which is 9.81, but for simplicity is often rounded to 10 meters per second squared, right? Now, you would have previously looked at the equations of motion for uniformly accelerated motion, and you would have basically applied these equations to the vertical direction. Now, let's look at the equations of motion which actually can apply in the vertical direction, and we're talking about those which basically involve or include the acceleration. So we have equations like, for instance, A, not A, let me not begin with A, but V equals U plus AT, right? That has acceleration in it. Another equation we have is V squared is equal to U squared plus 2AS. And we also have S is equal to UT plus a half AT squared. Now in these equations, of course, U represented initial velocity, A represented the acceleration, of course, and S would have represented the displacement, right? Now, since you're dealing with a vertical direction, we'll basically modify these equations to represent the current situation, right? So what will happen? As we said before, the A would be replaced by minus G, right? Now, as we saw from the body being projected, its initial velocity in the vertical direction will be equal to the vertical component of its initial launch velocity. So therefore, if its launch velocity is V, then this means its initial velocity U will now become V sine theta, right? What else can we modify? Because we're talking about vertical motion, then we'll use a symbol for displacement which is more reflective of vertical motion. So we can say that the symbol for S will become either Y or H, depending on which may be more appropriate, right? So sometimes you may see a Y being used for the vertical displacement as opposed to H, right? Occasionally we may use one or the other, or we may use both, but not simultaneously, right? So it may be Y or an H. And what else can we talk about? Now, U represents the initial velocity, and V could be the final velocity. And so since we're talking about this velocity in a vertical direction, then instead of V, we'll see that will become V with a subscript Y to indicate that we're talking about the velocity in the Y direction or in the vertical direction, right? Now, we will use these equations to derive certain commonly calculated properties of projectile motion. These include the maximum height reached, the time taken to reach maximum height, the time of flight, the horizontal range. And we'll also derive an equation for the path of the projectile, right? So let's proceed to doing that. So because we're no longer concerned with the horizontal direction, as this is all we need to know for the horizontal, let's just erase this and proceed. So let's look at the maximum height reached. So the maximum heights reached. Now, we've looked at vertical motion independently of horizontal motion before. And we know that basically, whenever anybody is projected vertically upwards, it rises to a maximum height and then it comes back down. But of course, before it comes back down, it will momentarily come to rest. So we know that basically, at the maximum height, the vertical velocity is equal to 0. So as we indicated there, at maximum height, the object is no longer moving vertically. And therefore, the vertical velocity or the vertical component of the velocity is equal to 0, right? So we'll use an equation which includes vertical velocity, and then we'll use the fact that at the maximum height, the vertical component of the velocity, or simply the vertical velocity, is equal to 0. Now, let's look at one of those equations. Now, in this case, what we want to find is the maximum height. So therefore, we must also use an equation which includes distance or displacement, and so on. And that equation is V squared equals u squared plus 2as, right? So we use that equation. So we use v squared equals u squared plus 2as. But of course, since we made these changes, then this equation becomes vy squared is equal to v sine theta all squared. Now a is equal to minus g, so therefore this becomes minus 2gh, right? Good? Then we say at maximum height, and let's call that h max, the vertical velocity is equal to 0. And so therefore what we have is 0 is equal to v sine theta all squared minus 2g h max. So from this we get that 2g h max is equal to v sine theta all squared, right? So let's just take these off. I'll probably drop them in a corner somewhere later on, right? So 2g h max equals v sine theta all squared, and from this we get that h max is equal to v sine theta all squared over 2g. In some books, the brackets would have been expanded, and so you may see that h max is equal to v squared sine squared theta all over 2g. And this equation, of course, allows us to calculate the maximum height reached directly, provided we have the initial launch velocity, v, the angular projection theta, and of course, you know the value of g. So this equation allows us to calculate the maximum height reached, h max. Good? Now, the next thing we will look at is what is called, well, the time taken to reach maximum height, right? So we'll look at the time taken to reach maximum height. So I'll put back our three equations in this corner here. We have the equations basically v equals u plus at, then we have v squared equals u squared plus 2as, and we have s equals ut plus a half at squared, right? So let's look at the time taken to reach maximum height. So the time to reach maximum height. Now, as we previously established, whenever the body reaches its maximum height, then at that point, the velocity or the vertical velocity is equal to 0. So it still has a horizontal velocity and it's still moving horizontally, but the vertical velocity, of course, is equal to 0. So we want to use an equation which includes vertical velocity and also include time, right? So writing it using our replacements, we could say that this equation would basically become Vy is equal to v sine theta minus gt. Likewise, this one we used before would have become Vy squared is equal to v sine theta all squared minus 2gh. And this one would have become, we can say h or y equals v sine theta minus a half gt squared, right? Now, time to reach maximum height. So we need an equation which includes vertical velocity and time, so we use this one, and so we can say that Vy is equal to v sine theta minus gt. But of course, at the maximum heights, the vertical component of the velocity Vy is equal to 0. And so we have v sine theta minus gt is equal to 0. V sine theta is equal to gt, and therefore t is equal to v sine theta over g, right? So if we examine this equation carefully, what we'll recognize is that v sine theta is simply the initial vertical component of the velocity, right? So I'll establish that the initial vertical velocity was v sine theta, and we divide it by g, we get the time taken to reach maximum height, right? So that's the time taken to reach maximum height. The next thing we look at is called the time of flight. Now, what exactly is the time of flight? Now, I left the diagram on the board for a particular reason. Now, the object is projected at O from some, let's say, ground level. It rises to a maximum height, and then, of course, it returns to A, which is at the same level of projection as O. So basically, what that means is that when it returns to the same initial level of projection, the next vertical displacement, of course, is equal to 0, right? So OA corresponds to the same level of projection, and when it returns to that level of projection, that means the net vertical displacement is equal to 0. And so therefore, to derive the expression for the time of flight, we will use an expression which includes the vertical displacement and, of course, the time as well, right? So that equation will be this one. So I missed out a t here, so this should have been v sine theta t minus a half gt squared, right? So the time of flight is basically the time taken for the body to return to its initial level of projection. So if it is projected from O, the time taken to return back to the same level of projection, that is the time of flight, right? So to calculate that, we use this equation, right? So we can say that h is equal to v sine theta times t minus a half gt squared. So we say that basically, when the object returns to the same level of projection, its net vertical displacement is equal to 0, right? So when it returns to its initial level of projection, the net vertical displacement is equal to 0, and therefore h is equal to 0, right? So I'll just write this in a shortened form. So when the object returns to, let me just write it out, its initial level of projection the net vertical displacement equals 0, right? So h, which could have been chosen to be y, and later on we'll actually use it, we'll replace it with y, represents the vertical displacement. So therefore it means that h would be equal to 0. And this time is called the time of flight. So we can say that 0 is equal to v sine theta, let's call it t with a subscript f for time of flight, minus a half gtf squared. And what we have on the right hand side is a quadratic in t, and we'll solve, right? So writing it like this, we have v sine theta times tf minus a half gtf squared equals 0. We can factor out the t, and so we get t subscript f v sine theta minus a half gtf is equal to 0. So having factorized it, we can then say tf equals 0, or v sine theta minus a half gtf is equal to 0, right? So continue with this piece. So bring this over to the other side. We see that now v sine theta is equal to, let's say, gtf over 2. We then multiply both sides by 2 and then divide through by g. We get that 2 v sine theta over g is equal to the time of flight, right? So therefore the time of flight tf is equal to 2v sine theta over g. Now let's compare this to the time taken to reach maximum height, and we should see a direct relationship between the two. The time taken to reach maximum height is given by the initial vertical component v sine theta divided by g. The time of flight, which is the time taken to return to its initial level of projection, is equal to 2v sine theta over g. So what this shows is that the time of flight is twice the time taken to reach maximum height. And what exactly does that mean? if projected from O, it takes a certain time to reach the maximum height, let's say 3 seconds, it must take the same time, 3 seconds, to return to its initial level of projection, and therefore its time of flight would be 3 plus 3, which gives us 6 seconds, right? So generally, for a body which is launched from some point O and returns to its initial level of projection, when it does so, the time taken would be equal to twice the time taken to reach its maximum height. Now, the next formula we'll derive is for the horizontal range. Oh, before we do that, now, in solving this equation, we got another value for the time of flight to be equal to 0. Now, what is the significance of this? What we're doing basically is we're finding the time at which the net vertical displacement is equal to 0. And for a body which is projected vertically or like this, some angle theta to the horizontal, there are 2 times at which the net vertical height or net vertical displacement equals 0. After it has returned to its initial level of projection, which we calculated here, and before it was actually projected. So T equals 0 or TF equals 0 corresponds to before the body was actually launched, right? So let's look at the horizontal range. And the symbol for that is usually an uppercase R. So on the diagram, if we were to represent the range, the horizontal range would be the horizontal distance OA. So this would be the horizontal range R, right? Now, we finally are going to be dealing with the horizontal direction. So if you remember, horizontally we said that the velocity is constant, and therefore distance traveled is equal to speed by time. So because we're talking about the horizontal direction, we can say the distance traveled, x, is equal to speed, vx, times time t. But the horizontal range is the distance traveled from O in returning to its initial level of projection, A. And the time that the object takes to do this is called the time of flight. And so therefore, to get the expression for the horizontal range R, we will say that R is equal to the horizontal component of the velocity times the time of flight. And so what we get is this. We get R is equal to V cos theta times 2V sin theta all over G. And we will simplify this. So V times V, that is V squared. So what we get is 2V squared sin theta cos theta over G. So this is the same thing as V squared times 2 sin theta cos theta all over G. Now for those of you who did math up to a certain level, additional mathematics or even pure maths, then you should recognize 2 sin theta cos theta based on trig identities. So 2 sin theta cos theta is equivalent to the sine 2 theta. So therefore we say that R is equal to V squared sine 2 theta over G. And this is a formula for calculating the horizontal range R, right? So basically for any angle theta, twice the sine of the angle times the cos of the angle would be equal to or equivalent to sine of twice the angle. And so this basically is a trig identity, and we're able to replace this with that. So the horizontal range is given by R equals V squared sine 2 theta over G. Now bear in mind that for this equation to be used, it must have actually returned to its initial level of projection. So the horizontal range formula is only applicable when the object has returned to its initial level of projection. If we only consider the motion up to a certain height, or if it actually falls below its initial level of projection, then this formula will not give us the actual horizontal distance traveled, right? So we'll try to remember that. Now, having done this, let's look at this range formula in a little bit more detail, right? Now, let's look at the formula. We have the range R is equal to V squared sine 2 theta over G. Now, theta represents an angle, and twice that value is also representing an angle. So, I mean, any angle multiplied by any particular factor is still an angle. Now, for any angle theta or even 2 theta, the range of sine lies between -1 and 1. So we say that for any angle theta, we say that -1 is less than or equal to sine theta is less than or equal to 1. And if we should actually even multiply that angle by 2, then these limits don't change. So -1 is still also less than or equal to sine 2 theta, which is less than or equal to 1. What does this mean? It means that basically that the maximum value that sine 2 theta can actually take is equal to 1, right? So we'll use this to find the maximum range. So we say that maximum range, or Rmax, occurs when sine 2 theta is equal to 1, which means that 2 theta is equal to the sine inverse of 1, 2 theta is equal to 90 degrees, and theta is equal to 45 degrees. And having found that, of course, this means that the maximum range, Rmax, is equal to v squared over g, right? So the maximum range is equal to v squared over g. So what this is basically saying is that for any launch velocity v, the range is a maximum when the launch angle or the angular projection is equal to 45 degrees. So if you're, for instance, kicking a ball, let's say it's a football, let's say it's a football, right? And you want to achieve maximum range, regardless of what your kicking speed is, to acquire maximum range, you must aim for an angle of 45 degrees. Any other angle will result in a shorter horizontal distance than that would have been if the angle was 45 degrees. So therefore, the maximum horizontal range occurs when the launch angle is equal to 45 degrees and is given by v squared over g. So basically, if we know a particular launch speed, we can actually calculate what the maximum range is likely to be when the object is actually launched at that particular speed, right? And of course, there are certain sports in which, you know, the range tries to be maximized and so on, and this of course comes in handy, right? So we looked at the maximum range. The last thing we will look at is basically the equation of the path, and we no longer need this, so we'll take it off. So let's look at the equation of the path. Now we've actually seen the path that the object took, which looks something like this. And at this level, we should know the name which is used to refer to paths that look like that, right? This, of course, looks like a quadratic function with a negative value of a. So if you remember, when looking at quadratic graphs or quadratic functions, say that if the coefficient of a was greater than 0, it was a smile, you know, something like that. And if it was less than 0, it is a frown. So this is normally used to remember the shape of the quadratic graphs whenever the value of a was positive or the value of a was negative, right? And to jog your memory, a quadratic, of course, is of the form ax squared plus bx plus c, where a, b, and c, of course, are real constants, and of course a is never equal to 0, otherwise it would not be a quadratic, right? So what we'll basically do is obtain an equation for the path and essentially show that it is parabolic, right? So to get an equation for the path, we will do this in terms of the horizontal distance x and the vertical distance y. Now this time we'll use y because, of course, you're very familiar with the x and y axes, and since these represent the body's distance moved in the respective directions, we'll use them. So for the horizontal direction, if you recall, we have the x, the horizontal distance, is equal to v cos theta times t, right? And for the vertical direction, the equation was, well, this one, but you replace h with y. So we have y is equal to v sine theta times t minus a half gt squared. Right? Now we want this equation in terms of the variables x and y. So to do that, we will basically eliminate t. To eliminate t, we'll make t the subject from this first equation, then substitute into the second equation, right? So from this equation, we see that t is equal to x over v cos theta. And we'll then substitute for t into this equation. So substituting t equals x over v cos theta, we get y is equal to v sin theta times x over v cos theta minus a half g times x over v cos theta all squared. Right? So we'll try to proceed, or we'll proceed and try to simplify this as far as possible. So we get y is equal to x times v sin theta over v cos theta, and this becomes minus, so we'll work this out. So this x, that gives us x squared, so this becomes minus g x squared over 2v squared cos squared theta, right? So v cos theta all squared, same thing as v squared cos squared theta. Now the v's here will cancel, and of course you know that from trig identities, sin theta over cos theta gives us tan theta, and so we have y is equal to x tan theta minus g x squared over 2v squared cos squared theta. Now we could proceed a little bit further with that equation, right? Most books do. And so what we have is, so we must bear in mind that we're basically deriving the path of the equation of the path. And we must bear in mind that the equation of a quadratic is of the form y equals ax squared plus bx plus c. So basically we want to get it in that form, right? So what we do is now we say that y is equal to, so let's put this term in front. So we get minus g over 2v squared cos squared theta times x squared plus tan theta times x, right? Now, in this equation, everything is a constant or as a fixed value except x and y. So we know the velocity, this is the initial launch velocity, that doesn't change. The angular projection doesn't change either, and neither does the cos of the angle nor the tan of the angle. In some books, this goes a little bit further because they use the trig identity that 1 over cos theta is equivalent to sec theta, and therefore 1 over cos squared theta is equivalent to sec squared theta. And so in other books, you may see this go a little bit further to write this as y is equal to minus g sec squared theta over 2v squared times x squared plus tan theta times x, right? So we say that all of this is a constant and tan theta is also a constant. So therefore, if we compare this to y is equal to ax squared plus bx plus c, we see that this is essentially the path of this is the equation of a parabola, right? So this is the equation of a parabola. And therefore we say that the path of the projectile is parabolic, right? But of course, we would have been able to tell this before based on the actual path. So we should be able to look at the path and tell that it's parabolic. But of course, we derive an equation which actually shows that it is parabolic. So this essentially, either version is accepted as the equation of the path, right? I'm trying to draw a little box here. Alright. So this equation of the path here, ax plus bx plus c. Alright, so so this is of the form y equals ax squared, rather, y equals ax squared. So y is equal to ax squared plus bx plus c. Of course, if you look at the path, then we see out that if this is our y-axis, this is our x-axis, the path is basically looking like that. So it passes through the origin, so therefore there's no c, there's no y-intercept, right? So this is the equation of the path, and it basically shows how the vertical displacement y varies with the horizontal displacement x, right? So in a situation where we only have, for instance, the angular projection and the speed, we can actually find the corresponding vertical displacement for a particular horizontal displacement x. So in this video, we basically looked at projectile motion. We spoke about what a projectile is. We spoke about the characteristics of projectile motion, and we also derive some of the common equations which are often used when dealing with projectile motion.